All right, so we are back covering U-substitutions, and the last video covered the intuition behind what U-substitutions are, and maybe something similar that we've seen in a previous math course where we made kind of substitutions to make our lives easier. And this video is going to cover basically working through some of those applications. Now, I will kind of warn you that if all you do is watch this video and you're like, oh, I just need to see a few examples and I'll just get it, you are correct. You will be able to kind of follow the steps of what it is that you're doing. But where you will lack is in that intuition and in that understanding. So do make sure that you've watched the prior video before you just try and do this one. Because let's be honest, right? The thing that's going to get you hired in today's society is not whether or not you can perform a U-substitution. A monkey could perform a U-substitution at this point, right? AI will perform U-substitutions for you. What will separate you is if you can explain what the heck a U-substitution is, where it came from, why it is that we're doing this in the first place, etc., etc. Those are the skills that are really going to set you apart. So just something to keep in mind kind of as you're working through this and as you're working through the rest of the class. All right, so in the last video, I brought up an example of taking the derivative where you were given the equation y is equal to, let's do the natural log of x cubed plus x. And we concluded that the derivative of this thing is 1 over x cubed plus x, but then times the derivative of the inside, which was 3x squared plus 1. And that's the derivative, right? This is just that's the derivative. So we can kind of tidy this thing up and say our total derivative is 3x squared plus 1 over x cubed plus x. Okay. And so now, right, now that we're in Calc 2, a very, reasonable question to ask would be to ask you to evaluate the integral of 3x squared plus 1 over x cubed plus x. So we're given this indefinite integral, which basically just translates for us, right? How do you solve an indefinite integral? You're just doing the antiderivative, but we don't yet know how to do this. And so the idea here is I think instead of me trying to come up with a whole bunch of rigorous steps, if you understand the intuition, I'm just going to run through this example, how I would do it with some logic kind of along the way. And I think the more examples you see, the more you're going to kind of get the hang of it. So the very first thing that I'm going to do is I'm going to recognize that if I look at this whole function, this whole whatever it is that's in here, that it looks like I have some bit of it, and I have that bit's derivative sitting in the same problem, okay? And so the very first thing I'm going to do in making this, I'm going to, recognize that it looks, right, it looks like the chain rule has taken place. And that's just like a mental note that I'm going to make for myself. Because that is what's going to inform me that I should probably try to use a U-substitution. And so the first thing that I'm going to do here, step 1, is I'm going to say, well, let's let U be equal to x cubed plus x. Okay, that's what I'm going to do. So let's put a box around this. Big important step. We're going to use our knowledge of the derivative to make an educated guess that I want U to equal x cubed plus x. Now, I haven't really described, why it is that we're doing this yet, but that's what this next bit's for. Okay, so let's make some space. All right, we're going to move this over. Probably going to take that P with me. That's okay. All right. Place. Okay, so the first step is we're going to let U equal x cubed plus x. And remember that I had tried to give the intuition that we're starting this problem off in what I called X land, right? We're starting off over here, and doing this integral as is very difficult. So trying to solve the integral of 3x squared plus 1 over x cubed plus x dx, sad face, very hard. And so I claim that if we go to a brand new land, if we go over here to U land, which looks bigger and better and more awesome, then our life is going to be easy, okay? Or hopefully easier. And so I said, well, let's let the car that gets us there be equal, u is equal to x cubed plus x. And so what does this mean for us? This means that if I am choosing this, right, I could have picked anything, but I'm making the educated guess that I want all of this to be equal to u, then my integral, whoops, not highlighter, my integral is now going to be, right, in the bottom I'm going to have just u, but in the top I still have 3x squared plus 1 and a dx. And right here we still have a problem. The problem is what? Well, the problem is that we're supposed to be in U-land, but we're not all the way in U-land yet, right? We're not there. We haven't made it to U-land yet, okay? And the problem is because we still have x's in our problem. And, you know, more specifically, like the most annoying one is the fact that if I'm going to do an integral, you know, with u's in it, then I better not have a dx here, right? What do I need to have there instead? I would need to have a du. And so, you know, our current problem, so step 2, is we need to, you know, get a du somewhere, right? Because otherwise we can't integrate. We can't integrate something with a u in it without having a du there. It's not possible. And so at this point, we're going to need what we really need. We need a relationship. We need a relationship between dx and du. And what I mean is, just like earlier, right, we picked u is equal to x cubed plus x. That's great. That transformed the bottom of this equation. But we don't have anything for dx, right? What we really need to show up is we need something that says dx is equal to blah in terms of u, right? This is what we really need. And this is where our knowledge of Calc 1 comes in, which is that we say, well, wait a second. We say, well, you know, if u is equal to x cubed plus x, right? Courtesy of our decision that we have made, right? If u is equal to that, well then, right, can I get a relationship between du and dx to kind of show up here? And well, hopefully that sounds a lot like taking a derivative, because if I take the derivative of both sides of this thing with respect to x, if I take the derivative of the left side with respect to x, and I take the derivative with respect to the right side of x, what do we get? Well, on the left-hand side, we're just going to be left with du dx. And on the right-hand side, we're going to be left with 3x squared plus 1. And you're like, okay, well, that doesn't really solve what we need because we're still trying to substitute out this dx. So we're going to do a little bit of mathematical rearranging, right? I'm going to multiply both sides by dx to get du is equal to 3x squared plus 1 times dx. And the very last bit here is that to get dx by itself, I would get that du divided by 3x squared plus 1 is equal to dx. And I'm going to put a little box around that. So that's going to be super important because we're trying to make it to U-land, and now we are going to finally be successful in our goal. Because over here, this pink circle, if you will, this is going to be U-land. And now we're going to have the integral, and in the denominator we have u, and in the numerator, like, wait a second, we still have this 3x squared plus 1. But at the very least, this dx, we can substitute it out with something that has a u in it. It's du over 3x squared plus 1. And again, you might say, well, wait, hang on a second. I thought our dx, we wanted it to be only in terms of u. It turns out that in this process, because we're making the very educated decision for picking our u, we're not really picking this at random. We're making an educated decision. This 3x squared plus 1 here, you'll notice, cancels out with the remaining 3x squared plus 1 that we have right there. And so what we've now accomplished is that this integral is really just the integral of 1 over u times du. So let's scroll back for a second, okay? So we started over here. We started in X land. Everything is difficult. We made an educated decision based on the fact that we're like, well, it kind of looks like the chain rule is taking place, right? 3x squared plus 1 is the derivative of x cubed plus x. So without really much explanation, I said, let's let u equal x cubed plus x. We did that, and we got to kind of like an intermediary step where we were kind of in limbo between u land and x land. And then we said, okay, well, we need to get something, we need to get a relationship that's going to turn dx into du. And we said, well, if u is equal to x cubed plus x, then we're going to get this relationship courtesy of the derivative that includes du's and dx's in it. And we finally got that dx was equal to something in terms of u. And, you know, it is actually still involved something in terms of x, but those things end up canceling, and they leave us with this integral. And so what does this allow us to do now? Well, thankfully, you know, last time I checked, the solution to this integral is just the natural log of the absolute value of u plus some constant c. And we have actually solved this integral. And so, well, the very last step would just be we just need to return back to x land. And we are just going to recall that our u was equal to x cubed plus x from earlier. And so that is going to get us our final answer of the natural log of the absolute value of 3x squared plus 1. Oh, no, not 3x squared plus 1. Absolute value of x cubed plus x plus c. There we go. Right? And this is going to be our final answer. And usually at this point, people just have one slight caveat, is that they said, well, in the example that I started with, I had originally given us the natural log of x cubed plus x, right? And I said, let's take the derivative, right? And the derivative was equal to, it was 1 over x cubed plus x times 3x squared plus 1. Well, just like in the other way, you know, going back, we get like a plus c to show up. We have experience now that in going backwards, if we're starting here, we kind of are slightly limited by the fact that the antiderivative of a logarithm, we need to have only positive values inside of this thing, right? We need to make sure, right? So maybe this is a good little aside. If you just start with the function 3x squared plus 1 over x cubed plus x, right? If I just start here, I don't know that this necessarily came from the natural log of x cubed plus x, right? If I knew that, then I would know that this starting thing has some restrictions, specifically like, you know, that this thing x cubed plus x has to be greater than 0. Right, because a logarithm has that restriction. But if I don't know that's where this came from, and I'm just given this problem, and I say, find the antiderivative, right? I say, take the integral of this thing. Well, if you just look at this fraction, there are no restrictions on what x can or can't be, with the exception that the denominator here can't be equal to 0. But there's nothing keeping it from being negative numbers, right? I could put in negative 10 for x. This whole thing could have a negative value. There's nothing stopping us from doing this. But when we solve it and we realize, oh, wait, right? Like the original function that this came from is the natural log of x cubed plus x, we have to say, well, wait a second, we can't have negative numbers in here. If we're just looking at this, the domain of this thing is like all real numbers with, except that x cubed plus x cannot equal to 0. But the domain of this is not all real numbers. The domain of this is that x cubed plus x has to be greater than 0. And so when we do this antiderivative, because we didn't know that information, we have to put these absolute value bars here to save our bacon. So that's why our final answer in this previous problem has, an absolute value of x cubed plus x instead of it just being the natural log of x cubed plus x. Okay, so this is just one example, and I feel like one example is not nearly enough for this particular material. So let's do another example. So let's do, so let's do the integral of, let's do 2x e to the x squared dx. Okay, so here we go. We're going to follow some similar steps, and we're going to look at this thing and say, well, I see an x squared, and I see that the derivative of x squared is sitting down here on the ground. Maybe I'll use a different color. The derivative of it is sitting right there. And so that is going to be my intuition that for step 1, I'm going to want to use a u-substitution, and I'm going to let u be equal to x squared, okay? So if we do this, right, we're starting off in x land. So I'll continue my drawing maybe for this last example. So we're starting off here, but the integral is pretty difficult, right? We don't know what this antiderivative is, and our goal is to make it all the way over here to u land. Okay, u land is hanging out over here. We're trying to make it there. U is equal to x squared. But we know that if I just, do that, I'm going to have an integral of 2x e to the u dx. That doesn't get us there, all the way, right? So we have integral 2x e to the u dx. We're not all the way in u land yet, so I'm going to kind of pop that out for a second. And now our next step, our step 2, was to recognize, okay, well, in order to compute any integral that has a u in it, we need this to be a du. So I need a relationship between dx and du. And so we're going to use that, if u is equal to x squared, then if I take the derivative of both sides with respect to x, I'm going to get that du dx is equal to 2x. And now I have something that I can start manipulating that's going to give me a relationship between du and dx. And at this point, if you're extra astute in your observations, right, you might notice that 2x dx is sitting right here in this problem. And so this kind of lets us know that that is just going to become our du. But if that's a little bit too advanced or too big of a jump, we're just going to kind of continue the steps that we did from the last example and just finish this up and get that du divided by 2x is equal to dx, okay? And this right here is going to be our transformation. This is going to help us get our dx into at least something that has a du in it. And so that's going to allow us to go from here and turn this integral into 2x e to the u times du divided by 2x. But now finally, because this 2x and this 2x are going to cancel, we finally arrive at u land and we get e to the u du. And we say, oh, well, what's the antiderivative of e to the u? Well, that's just e to the u plus c. And now we just go backwards. We're going to use this same transformation and say so that our final answer is just e to the x squared plus c. And there is our answer nicely worked out. And we could check this answer, right? If I tell you that y is equal to e to the x squared plus c, we can take the derivative by saying, well, the derivative of e to the anything is e to the anything times the derivative of what that thing is, so times 2x. And then the derivative of a constant is just 0. So we end up here, which is exactly what we started with. Okay. So this is a pretty solid example. But maybe, a question that people tend to have right now is, what if this first thing here isn't perfectly this derivative, right? What if we're off by a constant? Okay, and so what I mean is, let's take that same example, but instead of having the integral, we had an e to the 2x dx in there, or not e to the 2x, we had an e to the x squared dx. But what if this first term is like 9x? Okay, so we still, maybe have the intuition, right? All right, there's an x squared, and the derivative of an x raised to the second power is something with x raised to the first power. And so our little spider sense is tingling, and we're trying to, we're thinking that, okay, well, maybe this is still going to be a u substitution. And so we're still going to try it anyways. We're going to try a u sub all the same, okay? And if we do that, we're going to say, well, let's let u be equal to x squared. And in anticipation of the fact that we're going to need to convert this dx into du, we're going to say then we take the derivative of both sides with respect to x, and we get du dx is equal to 2x. We do a little bit of rearranging. Du is equal to 2x dx. And ultimately still land on that du over 2x is equal to dx. So as we're going over to uland to solve this thing, we now have the integral of 9x e to the u times du over 2x. And now you'll notice that the 9x and the 2x don't perfectly cancel, but they cancel enough in the sense that all we're going to be left with here is like a 9 halves. And these x's, that's the most important thing, is that those x's cancel out. And we'll have a 9 halves integral e to the u du. And we can still solve this the same way, which is that we're going to get 9 halves. Well, the integral of e to the u is just e to the u plus c, right? We get this. And remember that, you're going to multiply this into both, and the plus c just absorbs this 9 halves and becomes a brand new, bigger plus c. It becomes a brand new constant. So I'm just going to write it as 9 halves e to the u plus mega c if you want, right? So these c's are different. And at this point, now we go back to xland and we say that our answer to this is equal to 9 halves e to the x squared plus c, and we go home happy. And again, we could check our answer because the derivative of e to the x squared is going to be e to the x squared times 2x, and that 2 that we're going to get is going to cancel with this 2 in the denominator and leave us with the original equation. So in that shortcut that I mentioned in the last problem where I said, hey, look, you notice how, so in the last problem, we could say, well, look, du is equal to 2x dx, and I have a 2x dx sitting in my problem. So you could just make the jump from this if you wanted to and say that the integral becomes the integral of e to the u times du, because our du is equal to 2x dx. That works in that example. But in this particular example, it's a little harder to identify, because if you look at this and say, well, my du is 2x dx, you're like, oh man, I have a 9x dx. It may just be harder to make that substitution. You may not be able to just make the immediate substitution that, okay, the mental gymnastics that I could do to make this happen is if I have a 9 halves e to the u du here, then it works, right? That's a very hard step to take. So this is a good shortcut if it works, but if not, keep going, fully solve for dx, and do this whole process of substituting out everything out, and just kind of go step by step until you start to get more comfortable with u-substitutions. All right. So we're going to do one more example. I think it's a good example to finish on. So let's do, for example, the integral of cosine of x divided by sine of x dx. Let's do this example. And again, very, very natural. We might notice that, well, I have a sine of x here, and I know that the derivative of sine of x is cosine of x. So again, our intuition for step 1 is that we're going to let u be equal to sine of x. And that's because that's going to give us that du dx is equal to cosine of x. And with a little bit of finessing, we're going to get du is equal to cosine of x dx. And again, you could notice at this part that there's a cosine of x dx there, and that's going to just become du. But we're going to keep going to build good habits, and we're just going to say that du divided by cosine of x is equal to dx. And we're going to kind of maybe we'll circle this because those are the two we're going to use. And now we're going to head on over to U-land where we're going to solve this integral. So this integral now becomes, we have cosine of x divided by u, and then times our du over cosine of x. And lo and behold, because we're making good decisions with our lives, this is just the integral of 1 over u du. And the antiderivative of that is the natural log of the absolute value of u plus c. And so we're going to finish this off by going back to x-land, and we're going to make our substitution back in for u. And so we get the final answer is the natural log of the absolute value. What's our u? Well, u is sine, so natural log, absolute value, sine of x plus c. And this is going to be our answer. And again, we could check this because the derivative of the natural log is 1 over sine of x times the derivative of the inside, which would be cosine of x, and life is good. That's going to end up back here. And so what we basically just solved for, right, if you noticed, maybe you kind of said, wait a sec, this thing is the integral of cotangent of x. And yeah, that's the integral of cotangent of x. The strategy of turning things into sines and cosines still reigns supreme. But the reason why I brought up this example is because I wanted to do its sibling example, which was, what if I were to give you the integral of sine of x over cosine of x? So this one, maybe a little bit more famously, is the integral of tangent of x dx, right? How do we go about handling this one? And we could go about it in the same way. We say, well, there's a sine of x, the derivative is cosine of x. Let's let u be equal to sine of x. And so then we're going to get that our du dx is equal to cosine of x, right? The same stuff that we just did. And with a little bit of algebra, we're going to get that du divided by cosine of x is equal to dx. And so now you're going to notice something interesting happens, which is that when I decide to go to U-land to solve this integral, and I say, okay, I'm going to get the integral of u divided by cosine of x, and then I'm going to use the fact that I know that dx is equal to du over cosine of x. You're like, wait a second. This thing, we have a u. But now in the denominator, I don't have cancellation. I have cosine squared of x du. And at this point, we cry ourselves to sleep. If we do it this way, you're going to notice that we did not get cancellation. And that's because we made a very serious but very easy to fix mistake, which is that this is not just cosine of x, right? This is technically 1 over cosine of x. And the derivative of sine is not 1 over cosine of x. So the problem is that our du that we saw was in the denominator. And last time I checked, we don't have an integral of u over du or something like that, right? It has to end up as something as u multiplied by du. And that is like a little wrench in what it is that we're doing right now. We did not get the cancellation that we're looking for. And so this is a good place to write down in your notes, which is that if you do a u-substitution, and you go through, you solve for dx in terms of du, you put everything in, and you still do not end up fully in U-land, you have probably made a mistake in solving the problem, and you need to go back and either do a different substitution or try a different method. And so I'm going to do the first part. I'm going to take this, I'm going to shrink it, well, if it lets me, let's see, I'm going to take this, we're going to shrink it, and we're going to move it. Can I make this a little smaller? All right, we're going to move it over here for a second. Okay. And now we're going to say, well, the derivative of sine is cosine, but thankfully the derivative of cosine is negative sine. And so, since the derivative of cosine is just this, but it's just off by a constant, we saw in the last example that we can still have that, right? So maybe scrolling back up here, if I have an example like this, the derivative of x squared is 2x, and 2x is equal to 9x, just off by some constant, which ended up being, in our case, like 2/9, right? It's just, it's equal to it, but it's off by some constant. And we're kind of figuring out that is going to be okay. As long as the meat of this thing, which is the fact that the derivative of x squared goes down to an x to the first power, as long as that's met, we can deal with being off by a constant. So in this particular case, we're going to let u be equal not to sine of x, but we're going to choose u to equal cosine of x. And that's going to give us that du dx is equal to a negative sine of x. And we're going to very carefully rearrange things. So du is equal to negative sine of x dx. And that's going to give us that du divided by negative sine of x is equal to dx. But thankfully, now when I decide to go to u land, I'll have the integral of sine of x divided by my u, and then the fact that our dx is now going to be du divided by negative sine of x. And now the cancellation that we want to happen is going to happen. So we're going to end up with, I'm going to pull that negative sign out. We're going to get a negative integral. The signs will cancel, 1 over u du. And this thing is going to be just negative natural log absolute value of u plus c. And so to finish this off and to go back to x land, this is negative natural log u is equal to cosine, so absolute value cosine of x plus c. And that is a perfectly serviceable answer for the antiderivative, right? The antiderivative of tangent of x dx. And so before we finish, I'm just going to point out two quick things really quick, which is that one, in the textbook, another version of this is we can remember that we can move the coefficients of the natural log up and down from the exponent. So this is actually still technically equal to the natural log absolute value of cosine of x, but raised to the negative first power. And that's not arc cosine. This is good old fashioned, cosine raised to the negative 1. So this is actually natural log of 1 over cosine of x, which 1 over cosine is famous for being secant of x plus c. So these answers are the exact same, and you may see them and you can use them interchangeably. I kind of like natural log of the absolute value of secant of x, but you can do whichever you want. And then one more thing I wanted to point out, which was, with this method that we did earlier, where we made this mistake letting u be equal to sine of x. And the reason why it was a mistake is that we kind of end up here. We could, in theory, right, we could actually try to work around this by doing the following, which is we could remember that cosine squared, using our trig identities, is 1 minus sine squared of x. And I happen to know that u is equal to sine of x. So this integral here is actually the same thing as the integral of u over 1 minus u squared du, right? And we could try and see, can I solve this? And if we do this, we say, okay, well, let's see here. Do I see any derivatives sitting around? Yeah, actually, I see that if there's a u squared, the derivative of that is like 2u, which is kind of like this. And even better than choosing this to be our thing we're going to substitute out, the derivative of 1 minus u squared is still the same thing. And so it's a good strategy, actually, to pick the whole thing when possible. Pick the largest thing possible that you could substitute out when you're working with these problems. And so now we're going to do another u-substitution, but in this particular case, we've already used the letter u, so maybe I'll use the letter v. So we're going to say, let v be equal to 1 minus u squared. And then what we're going to get is that dv du is equal to negative 2u. This we can rearrange to get that dv divided by negative 2u is equal to du. And so that's going to allow us to rewrite this as the integral. We're going to have u over, now we made a substitution, we said 1 minus u squared is equal to v. And then we also made a substitution that du is equal to dv over negative 2u. And then from here, we get negative, let's see, we're going to have a 1/2 that we can pull out, if I haven't made any mistakes. And then we have integral of 1 over v dv. And this we can now actually solve, right? We can actually solve this thing. I'll zoom out a little bit so we can still keep track of everything. But this is negative 1/2 natural log absolute value of v plus c. And then we say, okay, well, what was v, right? Well, we have to take a pit stop at u-land, and v was equal to 1 minus u squared. So this is negative 1/2 natural log absolute value 1 minus u squared plus c. And then we have to go back and remember, okay, wait, what was the u that we chose for this particular example? Well, in this case, we said u was equal to sine of x. And so this we're going to get, this we're going to get negative 1/2 natural log absolute value 1 minus sine squared of x plus c. And this thing over here, let's see, is equal to, negative 1/2 natural log absolute value. Well, 1 minus sine squared is cosine squared of x plus c. And this thing's starting to shape up a little bit, because now I can use the same exponent rule, which is that this is the natural log, the absolute value of, well, if I put this up, I'm going to get a negative 1/2 in the exponent here. So that's going to give us a cosine to the negative first power of x plus c. We still end up at the natural log absolute value of secant of x plus c. So we still end up at the exact same place doing this first method. So it turns out that in this particular example where I was just like, dang, things didn't cancel out, we still have x's, we tried going to u-land, we failed, we should try something else. In this particular example, it turns out that you can get around it using some trig substitution, but it's still a good idea to go back and re-examine the problem and do what we did over here, which is, all right, let's see if there's any other derivatives that maybe we could make a good choice for. And in this case, like letting u equal cosine of x ended up working out because we were able to solve that problem pretty straightforward and get down to our final answer, which was in this green box over here. So there's a lot of stuff going on in this video. This video is super important and covers all the way from the very basics of u-substitution to some of the more intricate nuances of u-substitution, to ways that u-substitution can fail really terribly, and to ways that it can save us. I do want to reemphasize that u-substitution is only good for very particular types of integrals. It's not going to let us solve every single type of integral, but we do need to be, in order to be good at doing a u-substitution, you have to have your derivatives down really, really well. You need to know some of your basic trig identities. You need to know your derivatives of your logarithms, your derivatives of your exponential functions, things like that. Because if you don't know those, then you won't be able to recognize that these derivatives are sitting inside the problem, and then using, the u-substitution is going to be an incredibly hard task to accomplish. So that's going to do it for us in this particular video. We ran through a bunch of examples. Hopefully they were super helpful. And I think in the next video, we'll do maybe a couple more just brief examples of other ways that u-substitution can be used specifically with trig functions. And then we'll go on maybe to a new technique. So hopefully this was interesting, and I'll catch y'all in the next one.